Let's do this problem. Problem 37, chapter 5 on page 144. Let's read it. It says a car is traveling at 50 miles per hour on a horizontal highway. If the coefficient of static friction between the road and the tires on a rainy day is 0.1, what is the minimum distance in which the car will stop? B, what is the stopping distance when the surface is dry, where the static friction is 0.600? Okay. So here, drawn it out, our initial velocity of the car, it's 50 miles per hour. We're going to stop. How far does it take us to stop? Given, when the street is wet, it's only 0.1, and then when it's dry, the coefficient of friction is 0.6. So let's draw a free body diagram of the car. Well, actually, let's start with what we're trying to find. Let me do that. Here's what I'm going to assume. I can use forces to figure out what the acceleration is. So I have the acceleration, the initial velocity, the final velocity, and I want to know delta x. So I'm going to use the fourth kinematic equation because that one doesn't have time in it. So v squared equals v naught squared plus 2a delta x. So this is 0. So we can say that delta x will be equal to negative v naught squared over 2a. And we've seen this before. Now, you need to figure out what the acceleration is. And I need to let's just do this right now. What is 50 miles per hour? What's the unit conversion from miles per hour to meters per second?
How many meters are in a mile?
Oh, for heaven's sakes, you guys, look, I'm just going to do this one. And, oh, wait. Hello? Hi, Paul. Oh. How many, How many miles per hour are in a meters per second?
That would be 2.24 miles per hour.
So 1 meters per second. 1 meter per second equals 2.24 miles per hour. Thank you. Oh, thank you.
It is I who should be thanking you.
Oh, see? She knows. That was nice. Okay. See, I'm learning how to use technology. So miles per hour cancels miles per hour. We're left with meters per second. 22.3 meters per second. And there's also a unit conversion table in your book, but you can use that. So now we know what the initial velocity, this is the initial velocity, so we have that. But we need the acceleration, so let's draw the car. Here's the car. Got mg, got the normal force, and we have the force of static friction, holding it back. So we're going to say this is the positive x direction. There's the y direction. So if I sum the forces in the x direction equals ma, ma in the x direction. Well, I've only got one force in the x direction. That's the negative force of static friction equals the mass of the car, which I don't know, times the acceleration. That's what I want. But what is the force of static friction? It's mu times the normal force. And the normal force is just equal to the weight here, right? Because there's no acceleration in the vertical direction. So this is going to be negative mu times the normal force, which is just, let's just plug it in. mg equals ma. And we get this result a lot. I mean, when the friction is the force causing the acceleration, when it's the net force, the acceleration will just be equal to mu times the acceleration of gravity.
How do you get mg?
Well, remember that I skipped a step. Remember we said that the force of friction is equal to mu times the normal force, but the normal force is just equal to mg. because there's no acceleration in the y direction. And so now I can plug in. This is going to be negative mu. So the first part, it's 0.1 times 9.8 meters per second squared. Well, that's pretty easy. It's 0.98 meters per second squared. And so now delta x will be equal to negative 22.3 meters per second, square that, divided by 2 times 0.98 meters per second squared. There's a negative in there. The negative will cancel the negative, and we'll get a positive delta x of
253.7.
253.7?
Yes.
How about 254? We'll round that up. Is that right?
Yes. What question was that? Yes.
Yeah.
Oh, they have 256.
Oh. Huh. 256, I wonder if they rounded this off a little differently or something. Now, delta x for the next part, well, it's going to be negative 22.3 meters per second quantity squared over 2. Now, what is this acceleration? It's going to be 0.6 times 9.8. So in other words, a is going to be equal to mu, which is negative 0.6 times 9.8 meters per second squared. So what's that a?
42.3 or
0.42? 0.423?
Oh, no, the delta x.
No, I'm talking about the
Oh, the
acceleration.
acceleration 0.6 times 9.8.
Yeah,
5.88.
thought that was wrong. 5.88?
Yeah.
So the negative will cancel the negative again. So 22.3 squared divided by 2 divided by 5.88.
42.3.
So quite a bit less, huh? 42.3?
Yeah, and then the both we have 42.7.
Yeah, it's okay. Back of the book's slightly different. But remember, this last digit is uncertain anyway, right?
True.
So if it's a little off, that probably comes from, they probably didn't round this off as much as we did. Like the final velocity, if they didn't round it off as much, it can make a little bit of difference. But that's how you do it. And notice that when the roads are wet, you want to drive slower and be more careful, leave more room, because it's going to take you a lot longer to slow to a stop than if the roads are dry. And I don't know if it's that extreme, 0.1, that seems really, really low. I don't think a wet pavement road is really, it's probably like 0.2 or 0.3, but it's still significantly lower than when it's dry. So
Let me drive slower.
that's right. So be careful out there. That is all. Or das ist alles.